In 1996, the Nobel Prize in Chemistry was shared between three distinguished scientists: Rice University chemist Richard Smalley and Bob Curl of America, and Sussex University chemist Harry Kroto of Britain. The prize was awarded for the discovery in 1985 at Rice University in Houston, Texas, of a new form of carbon that possessed extraordinary qualities that promised to change the world of science and the world as we know it in significant and timely ways. The team discovered a molecule measuring a billionth of a meter in diameter, made of 60 carbon atoms, a molecule that spontaneously assembles into a hollow sphere of hexagons and pentagons, creating what is called, in the scientific world, a truncated icosahedron, and it looks exactly like a soccer ball. Because the arrangements of the atoms resemble two co-joined geodesic domes, it was called, or named, a Buckminster fullerene, or for short, a Buckyball, in honor of the famed architect and geodesic dome inventor, Buckminster Fuller. Of the discovery, Richard Smalley, in his 1996 Nobel Prize speech, said, "It was one of the most spiritual experiences that any of us in the original team had ever experienced. But it is not the discovery, but in discovering what carbon has in store for us. That is our destiny now. The only character of true genius in this story is carbon itself," according to Rick. Widely considered the earliest and most influential discoveries in the development of nanotechnology, the Buckyball became the team's Rosetta Stone, leading to the discovery of a whole new world of structures of pure carbon built on the nanometer scale. On June 22, 1999, Rick was offered an extraordinary window of opportunity to illuminate the capabilities and potential applications and critical importance of nanotechnology to America and to the world, this before the Congress of the United States, in which he emphasized the critical importance of establishing efficient public and private systems to make significant investments in the research and development of nanotechnology. These were his words. Mr. Chairman, I appreciate the opportunity today to present my views on nanotechnology. There's a growing sense in the scientific and technical community that we are about to enter a golden new era. We are about to be able to build things that work on the smallest possible length scales, atom by atom, with the ultimate level of finesse. These little nano things and the technology that assembles and manipulates them, nanotechnology, will revolutionize our industries and our lives. Everything we see around us is made of atoms, the tiny elemental building blocks of matter. From stone to copper to bronze, iron, steel, and now silicon, the major technological ages of humankind have been defined by what these atoms can do in their huge aggregates, trillions and trillions of atoms at a time, molded, shaped, and refined as macroscopic objects. Even in our vaunted microelectronics, in our highest tech silicon computer chip, the smallest feature is a mountain compared to the size of a single atom. The resultant technology is fantastic, but it pales when compared to what will be possible when we learn to build things at the ultimate level of control, one atom at a time. My own research these days is focused on carbon nanotubes, an outgrowth of the Buckyball research that led to the Nobel Prize a few years ago. These nanotubes are incredible. They're expected to produce fibers 100 times stronger than steel at only 1/6 of the weight, almost certainly the strongest fibers that will ever be made out of anything, strong enough even to build an elevator to space. In addition, they will conduct electricity better than copper and transmit heat better than diamond. Membranes made from arrays of these nanotubes are expected to have revolutionary impact on the technology of rechargeable batteries and fuel cells, perhaps giving us all electric vehicles within the next 10 to 20 years with the performance and range of a Corvette at a fraction of the cost. As individual nanoscale molecules, carbon molecules are unique. They have been shown to be true molecular wires, and they've already been assembled into the first single molecular transistor ever built. Several decades from now, we may see our current silicon-based microelectronics supplanted by a carbon-based nanoelectronics of vastly greater power and scope. It is amazing what one can do just by putting atoms where you want them to go. Let me give you just one personal example. I sit before you today with very little hair on my head. It fell out a few weeks ago as a result of the chemotherapy that I've been undergoing to treat a type of non-Hodgkin's lymphoma. While I'm very optimistic, this chemotherapy is a very blunt tool. It consists of small molecules which are toxic. They kill cells in my body. And although they're meant to kill only the cancer cells, they kill hair cells too, and they cause all sorts of other havoc. Now, I am not complaining. 20 years ago, without even this crude chemotherapy, I would already be dead. But 20 years from now, I am confident that we will no longer have to use this blunt tool. By then, nanotechnology will have given us specially engineered drugs, which are nanoscale, cancer-seeking missiles, a molecular technology that specifically targets just the mutant cells in the human body and leaves everything else blissfully alone. To do this, drug molecules will have to be big enough, thousands of atoms, so that we can code the information into them of where they should go and what they should kill. They will be examples of an exquisite human-made nanotechnology of the future. I may not live to see it, but I am confident it will happen. Cancer, at least of the type I have, will be a thing of the past. Mr. Chairman, honorable Congressman, I believe that it is in our best interest to move boldly into this new field. Richard Smalley sat there in front of Congress with no hair as a result of the chemotherapy and talked about the promise of nanotechnology for cancer and other diseases and how continued research will lead to breakthroughs also in information technology, advanced manufacturing, medicine and health, environment and energy, and national security for this and future generations, and how it would pay off for his children and children all over the world. In response to Rick's testimony and proposal to the United States Congress on that day in 1999, the United States launched the National Nanotechnology Initiative, a sweeping federal research and development program that coordinates the nanotechnology efforts of nearly 24 federal agencies, including the National Science Foundation, the Department of Defense, and NASA. The initiative's federal spending topped $1 billion in 2005, and the initiative's supplement to the President's 2011 budget will be nearly $1.8 billion for nanotechnology research and development. Professor Smalley's accomplishments as a scientist were formidable, but his contribution to society is best measured by his passion that science can and will deliver a better world. In the final month of his life, Rick stated with enthusiasm, "This is a magnificent time to be alive, to see these things happening in medicine and in so many other fields, and in my case, to have the privilege of being a scientist in this golden era of science. My own work is in a magnificently flowering mode right now. We just announced with NASA a new armchair quantum wire, a continuous cable of Bucky tubes that we expect will conduct electricity 10 times better than copper, yet have only 1/6 the weight, a zero coefficient of thermal expansion, and a tensile strength greater than steel. If we succeed, we will be able to rewire the world, replacing aluminum and copper in virtually every application and permitting a vast increase in the nation's electrical grid. That and the development of plug-in electric hybrid vehicles will enable us to wean ourselves away from gasoline for the bulk of our urban transportation needs, free us from dependency on Middle Eastern oil, and greatly improve air quality in cities throughout the world." Rick emphasized that energy is the most important problem facing humankind today. He said the overwhelming need for new sources of clean energy in the next 50 years, energy that can come only from undiscovered technologies, means the fate of human civilization rests with the next generation of physical scientists and engineers. The United States needs a national program on a par with the Apollo moon missions that will excite future generations about science and encourage them to become researchers. The message was simple. Rick liked to say, "Be a scientist. Save the world."